very happy to be here and share, I guess 3 different stories about black holes. I decided to do that because, being online, it's difficult to remain focused. So if you get lost somewhere during the first part, you can always pick up again during the second part and, hear another nice story about black holes. So, right, we live in incredibly exciting times from the perspective, at least from gravitational wave astronomy, because we have many observations, which means that indeed we get to test general relativity and the nature of the objects that we see. But of course, the key question is, how much can we actually test and how much can we actually learn from these observations? And one of the tools one of the key questions that we want to ask is, these objects that we see, many of them, we think that they're black holes, but they might very well be something else, right? They might be, boson stars or other Broca stars, the things like Peter talked about earlier today, that mimic black holes, but are not quite like black holes. So how do we know for sure that the LIGO Virgo events that we've seen are truly emitted by black holes? So one of the ideas is to use the multipolar structure of the Kerr black hole. And in particular, at the moment, right, we cannot quite measure the multipolar structure of the Kerr black hole that well. But in the future, these tests are going to get better and better. And in particular, right, once LISA goes online, we do hope to see, if we see a particular set of sources, we do hope to see many of the multiple moments of the Kerr spacetime. So key question is, of course, if we do measure the multiple moments of these sources, again, what does it tell us about the sources? Like, how well do they constrain what the objects are? And multiple moments, we love them, right? We have used them in many fields of physics, right? We use them all the time in electromagnetism, Newtonian gravity as well, right? Where we have these internal multiple moments that decay as the radius gets large, and the external multiple moments that grow with the radius. And also in GR, we like multiple moments, although of course the story there is slightly more involved because typically, completely generically, you cannot quite define what the multiple moments are. They only exist if the spacetime is stationary. But nonetheless, if the spacetime is stationary and you have some additional conditions that hold, you do get to define, for instance, the Garage-Hansen field multiple moments or the Thorne multiple moments. And in fact, it has been shown that these two are equivalent. So let's zoom in a bit on the GR case, right? Because what we really want to see if the Kerr multiple moments are unique, right? Because that would then help if we are able to see in observations all the, ideally all the infinite multiple moments, but of course, observations are not going to give us infinite multiple moments, but the subset, if they match all the ones of Kerr, can we then really say that it is the Kerr spacetime? That's the key question, right? And there's some beautiful results in the math literature out there that tell us that the multiple moments characterize stationary, axisymmetric, and asymptotically vacuum spacetimes uniquely. And in particular, this implies that if you have a vacuum spacetime with all multiple moments equal to those of the Kerr spacetime, it is in fact the Kerr spacetime. As a general relativist, someone really that loves the Kerr spacetimes, it's just such a beautiful, simple, well, to some extent, simple solution to GR, right? You don't want the multiple moments to just be unique, right? In fact, you want them to be special in some sense. And this has motivated some people to put forward this minimalist conjecture. So the idea that the multiple moments of Kerr aren't just, unique, but special in the sense that if you compare the multiple moments of any other object, they're always going to be larger than those of Kerr. Of course, when you take the absolute value. So in particular, some numerical evidence was provided for that, where people compared the multiple moments of, say, fuzzballs to those of the Kerr spacetime, where they found this to be true. And also there was some additional evidence from, a completely surprising corner, with all these scattering experiments that Michaela also implicitly talked about, with scalar fields that showed that indeed, in some ways, it looks like the multiple moments of Kerr are special and minimal. But in fact, we know this cannot be true. So this is not true. Why not? Well, we know that the gravitational field is more than its multiple moments. If we just look at Newtonian gravity, right? If I know the gravitational field, of course, I can determine all the multiple moments, right? I just go and calculate it. But even if I know all the multiple moments of my field, I do not uniquely know the gravitational field. So the second, arrow is actually, in fact, incorrect. You need to put additional assumptions, add extra assumptions to, be able to make that arrow to determine the gravitational field. So to make this excruciatingly, explicit, what we decided to do is to construct, not in the full general relativistic case, but in a simpler setting, in Newtonian gravity, construct Newtonian objects that have exactly the same multiple moments as those of the Kerr spacetime. And in fact, this can be relatively easily done. So this shows that, clearly this second line is not true. You need additional assumptions to make that claim. So in particular, right, if we want to construct Newtonian multiple moments equal to those of Kerr, we need to know Kerr's multiple moments, and they're given here. So if we look at the mass multiple moments up here, we see that they are indeed uniquely, as we know from the O'Hare theorem, specified by the mass and the spin, and then, a bunch of numerical constants. They're not particularly interesting, but you can calculate them. And what you see is that the mass multiple moments are only non-zero whenever in your harmonic decomposition, L is even, and they're all zero whenever L is odd. And that has to do with the, the symmetry in the equatorial plane of the Kerr spacetime. Now, we also, of course, in general relativity have spin multiple moments, so they have to do with, the motion or the rotation of the object, right? And there the reverse is true, so they're only non-zero for L equals odd. And again, they only depend on the mass and the spin and, some numerical constant. So we said, okay, let's look at a very simple model. Say, let's consider a Newtonian thin shell with some radius, capital R. If we decompose its mass density into spherical harmonics, and we say that these, coefficients have this particular form, right? So they are axisymmetric in a way, but not completely isotropic, right? Because they do depend on L, and they're different for different L. But we take it of this particular form, then all the Newtonian multiple moments, mass multiple moments, are identical to those of the Kerr spacetime. Now you may say, okay, how does this, I have very little intuition for, how this looks, right? So how does, this mass density profile look? Well, of course, like I said, right, it will depend on your angle theta, and it has this particular shape. So whenever the spin, this value of A over R is small, it is more isotropic, so to say. And
से बचाव और अधिक जानकारी के लिए आरोग्य सेतु ऐप डाउनलोड करें। देश में खाद्य सुरक्षा के ये सिपाही भोजन की निरंतर उपलब्धता को
anyhow, I'll just continue. So you'll see that, as you increase the spin value to larger values, it becomes more and more, the mass density is more sharply peaked and more concentrated near the equator compared to the poles. You should note, right, that also this mass density is, well, it is whatever it is. It's not isotropic, but, It exists, and it is always positive, as long as this ratio of A over R is less than this particular value, which is, some numerical value that you can just calculate what it is. And it's not so strange that, at some point, right, if you push beyond it, your mass density profile will become negative, but that's, not so strange, right? Because that also pushes you into the relativistic regime. So at that point, you shouldn't really be working with the Newtonian model, but you should start incorporating post-Newtonian and relativistic corrections. Now, you may say, okay, weird profile, I don't like thin shells, give me some other profile. Sure, we can do that too. So for instance, if you choose a constant radial profile with almost identical rho LMs, in fact, these are identical to the thin shell model up to this numerical factor, then again, you'll find that the mass multiple moments of this model are equal to those of Kerr. You may say, okay, I don't like constant radial profiles. I want some decaying profile. You can also do that, right? So you can look at, say, I don't know, we've explicitly constructed the model with, say, a sort of a cosine dependence. Again, same story. Now, of course, the Kerr spacetime doesn't just have mass multiple moments, but also spin multiple moments. And this is the formula for it. So and in order to calculate it, what you need to figure out is essentially how fast this object is spinning around this axis, which is determined by this V. I will not go into details how to calculate it, but you can do it. And if you expand your solution in terms of A over R, you get a profile that looks like this. And, we can essentially push this, to any order we like, as long as you're patient enough to calculate it. And if you do that, of course, again, the Newtonian spin multiple moments are identical to those of the Kerr spacetime. In fact, actually, this velocity profile is the same for both the constant radial profile and the thin shell model. And what you see is that also in this case, it's not isotropic. It's axisymmetric, of course, but it changes. It's zero at the poles, and then it becomes either maximized near the equator, or as A over R gets large, it has this particular interesting shape. And what you see again is also this nice feature, or this physical feature, that this velocity is always less than 1, right? Meaning that we're not going faster than the speed of light, so we're staying within this Newtonian regime. So just to summarize this first part, the essential takeaway message is, don't mistake an if statement for an if and only if statement, essentially, right? It is very tempting to think of the Kerr multiple moments as being unique and completely determining the structure of your space-time. But if you measure the field multiple moments, it does not uniquely determine what your central object is, right? You need additional assumptions. And we made that very explicit, right, with these two Newtonian objects. And we also have given an algorithm how to go beyond the Newtonian limit and do this iteratively for post-Newtonian corrections. Of course, you may object very fairly, like what is the what is the formation mechanism for your objects? They seem kind of contrived. How physically plausible are they? Are they even stable? But my key point is, right, there are no laws of physics or of nature preventing these objects, right? They satisfy all these nice energy conditions and everything. And we should just be very, very careful whenever we make a statement about what we see in our data and what we conclude about what the source is. Right? So whenever we add, I'm very happy to, if I see a gravitational wave source with multiple moments equal to those of the Kerr spacetime, I am also very happy to say, well, most likely it is a Kerr black hole and not one of these objects that I just showed you. But in order to make that statement, one should add extra physical conditions and right, make these assumptions very explicit. Now, this brings me, or these multiple moments, we can actually measure very well in a particular system, which brings me to the next topic. And that system is called an emery, an extreme mass ratio.
Can I ask you, sorry for the interruption.
Yeah,
can
please.
I ask you one quick question? So these are non-relativistic objects whose multiple moments, all the multiple moments matches with the car, right?
Yeah. Yeah.
But the beginning statement you show that if that statement that if for vacuum solution, if all the multiple moments is that of car, it should be car solution. But is it for relativistic object, right?
Yeah, that's for relativistic objects, and for the additional assumption.
I see.
You have a vacuum spacetime everywhere.
I see.
And well, then you can do that, right? But I mean, maybe.
I see.
So that's a key assumption that you put in, and then it's true. But if you don't put in that assumption, then that statement is no longer true.
Oh, I see. Thanks.
Thank you for your clarifying question. Very nice. Any more questions about part one?
Yeah, so is it easy to specify all the physical conditions that one should mention when, suppose we take gravitational waves and decode from their multiple moments?
Yeah.
So what kind of carefulness I should exercise in order to derive that fact that it is actually characterizing the source?
Yeah, that's a very, very good question. Yes, good question. Well, one of them is that right, in order to interpret any of these statements, you probably have to say, well, you know, I am assuming, first of all, that general relativity holds in the first place, right? And then on top of that, right, you have to be willing to make statements like, well, and I have not proven any of these things, right? But you have to put some additional constraints on the type of matter sources you allow. And then I'm not exactly sure what the input is or to prove hard, rigorous mathematical theorems, but yeah, more work needs to be done to make that more precise.
You said matter. I have to specify what kind of matter sources I'm considering.
So
why does that matter?
Yeah, because well, if I have a vacuum spacetime everywhere, if I can claim that, then you can claim that if you measure all the multiple moments equal to those of Kerr, that it is the Kerr solution. But if you have something, like a black hole mimicker, or other things, then it can be, or my Newtonian-like object, right? I just know the multiple moments and look at them, then these objects are indistinguishable. Right. But I could say, I don't, I look at my data and I say this can only come from vacuum. I somehow have some additional information that I know this. Then you can make that statement that it is, but then, if I measure all the multiple moments equal to those of Kerr, then it is the Kerr spacetime. Yeah.
Okay, right.
Of course, right? I don't know. We don't know that these are vacuum solutions, right? That's one of the things we want to test.
I mean, there is another approach to multiple moments where it's a self-force approach, where you take a compact object. It's not a black hole. You take a compact object, and then there is a framework of computing multiple moments to all orders in a non-perturbative manner. There is a definition, and then you can add self-field to that. This full construction is not fully understood in the context of gravity, but up to electrodynamics, I think there is a proposal for the framework. So in those cases, you would say this issue is an open issue. Like when I receive a radiation, and if I'm able to decode multiple moments, that I cannot settle that as a property of the sources. I
Yeah.
have to do some more work to
Yeah.
argue that that is a reasonable conclusion. That's what
Yeah.
you're saying.
Yeah, exactly. That's
Okay.
my statement. Yes.
Okay. Okay, fine. Thank you.
Thanks. Okay, so let me go on to story 2, which is about resonances with black holes. And indeed, they are in the setting of these MRIs that I mentioned, so these extreme mass ratio in spirals. So they describe a central massive black hole of 10 to the 5, 10 to the 7 solar masses, orbited by a small black hole of, say 10 to 100 solar masses. And typically, right, we model these systems as being isolated. But we asked ourselves the question, okay, what happens if we have another small black hole or other stellar compact object nearby? How does it even influence this MRI system? And the answer is generically, right? Actually, you don't need to worry about this third guy, this perturber, because you can say, well, this third guy, it's far enough away. I don't need all the fancy GR techniques. I can get an estimate using Newtonian gravity. And then you can argue that the influence of this third object on the MRI is indeed negligible. Of course, for that, to conclude that, you need to put in some reasonable astrophysical distance for this third object, right? So of course, as long as you put it close enough, then the third object is going to matter. But we, looked into the literature and we found that, well, although we don't really know these things, right? We don't have any concrete observations very close to these massive black holes yet. We, based on theoretical models and all these things, we can estimate that, we should expect these third bodies to be roughly at, 10 AU from such a central object. And in that case, right, as I said, don't worry about the third guy generically, except of course, when you have a resonance. So just, a one-on-one back to, what resonances are. Resonances occur when you have a matching of frequencies, right? So the canonical example is, of course, if you have some sound waves, you can sing very well, keep your pitch, and not like me, you keep your pitch very well and you have some wine glass nearby. If you match the natural frequencies of the wine glass, right, you can very efficiently transfer the energy in your sound waves to mechanical vibrations, which can lead to, quite drastic effects, such as, the shattering of your wine glass. Now, in the MRI system, you may ask yourself the question, okay, which frequencies are the ones relevant in this case? And as you know, if I think of the just of the MRI, if I think of the Newtonian case, if I have a two-body object, right, I just have one frequency, right? Because I can always go to my center of mass frame and I just have my, so to say my omega or omega 5 if you want. But in GR, right, this MRI system, is highly relativistic. We in fact have, or we need 3 frequencies to describe the orbit of the small guy going around the central one. As you can see, of course, if I'm far away from the central black hole, right, so whenever my semi-lattice rectum is large, these 3 frequencies are essentially the same, right, just as in Newtonian gravity. But as I get closer to the central black hole, these 3 start to be different and, get more and more different as I get closer to plunge into the black hole. So a resonance can happen, right? If I look at, say, one of the key parameters to describe the orbit, which is its angular momentum, it is roughly constant over long time scales, or fairly long time scales. But if a resonance happens, right, which involves these 3 frequencies that describe the orbit, and in particular, here, this M, K, and N have to be integer values, right? So, 0, 1, 2, 3. Whenever this condition occurs, you get something like a jump. So, whenever this happens, these resonances, or whenever these frequencies are commensurate, as they say, then the effect of the third object actually does become important. So in the rest of this, little story, I'm gonna answer the following question. So, why is this the resonance condition, right? Why does it involve these frequencies? How to calculate the size of this jump, right? And the third question, what is the effect on the waveform? Can we actually see this jump? Yes or no? And the answer to the third question, I already tell you, yes, we can see that, and we should model for it. Now, in order to describe all of this, I'm going to make my life a little bit easier, and I'm going to forget about the third guy for now. And I'll put it back in, but we'll see that, the framework I'm going to build up now is mathematically very adaptable, and we can, at the end, very easily throw in the third object and see that everything sort of goes through as well. So in particular, there are many ways to describe the orbit of the small guy, but one of the ways to do that is to use action angle variables. And that's particularly convenient in this context. So we know that, right, to zeroth order, right, if I sort of say, the mass of this small guy is so small it's negligible, then of course it is just following a geodesic, right? Because we know test particles in general relativity follow geodesics. And since the Kerr spacetime has 4 constants of motion, the geodesic equation is in fact integrable in this case. Now, if you write that in terms of action angle variables, you'll see that these actions, which essentially you can just think of, some linear combination of the 4 constants of motion, are absolutely conserved along the geodesic, and the angles just evolve at this constant rate determined by these orbital frequencies. So when I talk actually about omega r, omega theta, and omega phi, these are, these frequencies. So before I start introducing the perturber, you may object and say, hey, wait, but the motion is not geodesic. And that's actually right? Because we know that at some point, this small guy is going to get closer and closer and spiral inwards to the central massive black hole due to gravitational radiation, essentially, right? So gravitational radiation changes the description. And in fact, this goes by the name of cell force. Of course, there are also conservative effects, but radiation is typically more dominant. So in that case, right, we see, first of all, there's this nice thing, right? And that's the reason why action angle variables are quite useful, is that these formulas are changed, but we have a small parameter, which is the mass ratio. So the mass of the small object over the large object. And what we can do is, right, we can perturbatively include these corrections, which are the cell force corrections, to these the description of the action angle variables. Now, these formulas in general are very complicated. It's very difficult to calculate, but their form essentially just only depends on the angles q theta and qr, and not q phi because of the axis symmetry of the Kerr spacetime and these constants of motion. Now, luckily for us, we don't, to zeroth order, right, we can make a further approximation. So we don't need to know all the details of these functions, but we can make an adiabatic approximation, which essentially, roughly, if you think of, is sort of, a kind of orbit averaged approach over a few orbits. In that case, you can just say that the angles still evolve at a constant rate, roughly, and the actions will change, but only by the average of this function. So you don't need to know all the details of the function, but only sort of its average behavior. And the way to calculate this average behavior is to use the fact that these are proper angles, right? So these go from 0 to 2 pi, and you can then do a Fourier decomposition. So this is quite nice, of course, because once you have such a Fourier decomposition, you can say, hey, wait, when I start averaging, essentially, right, this is just an oscillatory function. So when I average, all these terms are going to drop out, and only the terms that do not oscillate will contribute to my average. And of course, the terms that do not oscillate are the ones where k and n are integer. right? So, or integer and 0, right? So because in that case, you just get this term just becomes 1 and it doesn't oscillate. Now, this is generically true, except of course, when, like I said, this term doesn't oscillate, or in other words, right, when its time derivative, which is just simply given by, right, the time derivative of q theta by definition was omega theta, and the time derivative of qr was omega r. So whenever this is 0, of course, that exponential is also not oscillating, right? So whenever these frequencies become commensurate, you do not, when you average out, you shouldn't just look at the 0, 0 piece, but also the coefficient corresponding to the integers k and n for which this is true. So to see sort of this pictorially, if we first look at the left picture, right, and we look at some generic evolution, this looks, I don't know, fairly messy, not very informative. But if we now project this orbit onto the r theta plane, what we see is that, you know, over long times, I'm essentially, right, filling out this complete r theta plane. Right? And that's the reason why averaging is sort of a good idea, because you sort of are mapping out, you know, completely this r theta plane. However, right, when a resonance happens, we can first look at the left picture. I may say something like, oh, well, maybe it looks less messy, but I know it's hard to tell. I think if you just compare the pictures on the left. But if you now look at the right figure, right, and look at its projection onto the r theta plane, it's striking, right? It doesn't matter how long we wait, we do not fill out this r theta plane completely. We're just restricted to this one-dimensional subset. And that's also the reason why averaging typically is not a good idea, right? When you are on a resonance, right? Generically fine, but not when you're on a resonance. So these resonances, right, that occur because of essentially the cell force, you may ask yourself the question, okay, are they astrophysically important, right? I mean, maybe they're just mathematical oddities and whatever, you don't need to worry about them. But what others have shown is that they indeed generically happen for MRIs, also in the Lisa band, that the jump size is typically small, but if they occur early in the in-spiral, they can lead to significant dephasing of the waveform. And in particular that, you know, they're more important whenever you have lower order resonances. So whenever the n and k, those integers are small. This is in fact is pretty much generically true for any type of resonance. You want your integers to be small for them to be important. And they also showed that they're more important for eccentric orbits. Luckily, in the case of cell force resonances, the conclusion is, although still somewhat tentative, but you would only lose a few percent for detection purposes, but of course they are very important for parameter estimation. Now, how about that tidal perturber, right? What changes in this story if I start to include it? Well, the nice thing about these action angle variables is, right, I can quite easily add them on, right? So now, right here, I have my cell force again, but now I'm adding here the effect of the tidal perturber, right? Which is also scaled with, you know, some small parameter epsilon, where here is the mass of the tidal perturber, the mass of the central massive object, and the distance of the central object to the perturber. So, right, this is essentially just the scaling of the tidal force. Now, there's one important thing to note, and that is that these functions now depend not just on q theta and qr, but also on q phi. And that, of course, has to do with the fact that, right, the Kerr spacetime is axisymmetric. But if I start to include a third perturber, that, of course, breaks the axisymmetry. So unless you were to exactly put the perturber along the spin axis of the black hole, right? But generically, all right, this breaks the axisymmetry. So you now have to include or work with functions that also depend on q phi. Now, if we start to do this adiabatic approximation again, we only need to worry about the average of this term. And when we do that, right, we again, we'll use the fact that we can nicely use Fourier decomposition. And we see now that in our Fourier decomposition, right, it's more general, right? We need to include this Q phi terms. So that's the reason why this resonance condition now involves not just omega theta and omega r, but also omega phi. So this is a more general condition, right? These tidal resonances are more general than the self-force resonance, because I have a whole extra dimension, so to say, to satisfy this constraint. And you can argue and see that they also occur for low eccentricity orbits, whereas that's not the case for the self-force resonance. Now you, just as in the self-force case, you may ask yourself the question, okay, fine, but does this actually ever happen during a generic in-spiral? Is it relevant? And in fact, the answer is yes. For instance, if I look at a prograde orbit around a spinning black hole of, say, 0.9, with dimension spin parameter 0.9, and I start out at, say, the semi-lattice rectum of 9-ish and an eccentricity of 0.7, right? And I evolve and get closer to the central black hole because of, well, say, the self-force, right? So my semi-lattice rectum will decrease, and as you know, also from, say, Matthews and Peterson, orbits in GR typically circular, right? So the eccentricity, right, will go down. And as I evolve and get closer to the central massive black hole, I hit all these lines, right? This line, this line, this line, that line. Those are the lines where low order resonances happen. In particular, right, when k is equal, in this case here, the first one is when k equals -3, m equals 0 and n equals 0 and m equals 2. And similarly here for these other resonances. And this, it happens for prograde orbits, but, also retrograde orbits. The location of the resonances shifts. Maybe the type of resonance you will encounter will be slightly different. But the point is, you have many of these surfaces and many of these resonances that you'll encounter. And they really happen across the parameter space, right? So here I showed you for like fast spinning black holes, but they also occur for slowly spinning black holes, right? So resonances happen across the parameter space. Now, of course, the next key question is, what's the size of the effect? And the way to calculate that is essentially to think of the tidal force as, accelerating your embry. And the way to calculate that is to look at the metric of a tidally perturbed Kerr, which is this h, which goes in here, and take the appropriate covariant derivatives with respect to the Kerr metric and do the right projections, blah, 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 blah. Luckily for us, we didn't need to calculate the metric of the tidally perturbed Kerr, but that was already specified for us in the literature, and was done using, or was obtained using the Tucholsky equation and metric reconstruction afterwards. Now, of course, we don't have the tidal force for a completely generic setup, right? So in this case, actually, we assume that the tidal field is stationary over the duration of the resonance. Of course, right, the third object will be moving around the central massive black hole, right? It's not just hovering there, but on the time scale of the resonance, we're assuming it's stationary. And we only assume that it's, that its leading order contribution is only given by its quadrupolar tidal field. And then we can calculate the jump size of the resonance. And that depends on, essentially two key things: how long the resonance lasts, which is in fact actually completely determined by the radiation reaction time scale. So as the embry is evolving, right, it will still keep on emitting gravitational waves, and the fact that it does that means that it will not, be locked into resonance, but it will slowly evolve through. And that scale is set by the radiation reaction time scale. And the strength of the resonance is, of course, set by this ratio of the mass of the perturber to the distance to the central massive object, its sky location, so whether it's, say in the equatorial plane or closer to the spin axis, the parameters of the central massive black hole, so its mass and spin, and where during the whole in spiral, right, the resonance occurs. So those essentially depend on the parameters of the emery. So what is its semi-lattice rectum at the resonance? What is its eccentricity? And what is its inclination angle? Now, for now, I'm going to ignore sky location because it does not, or it's not super sensitive to sky location, as it turns out. And I will show you a few cases where we've calculated the jump for a given spin parameter, eccentricity, and inclination. Now, the nice thing is, in fact, right, I should also tell you how it depends on m and this ratio m over r cubed, but as it turns out, those completely scale out of the problem, right? So they will be an overall factor. And of course, because when I'm on resonance, I also don't need to worry about p, because when I am on a given resonance, I know, right, that's an additional constraint to be on a resonance. So if I know these parameters, I also will know the value of the semi-lattice rectum. And in particular, right, for instance, if you look at some, say, a prograde orbit with this particular type of resonance and this particular type of inclination angle, you see that the angular momentum, right, so one of the ways to describe the orbit, is changed by a given amount depending on the eccentricity, which is a bit higher for larger eccentricities, but not significantly larger. And also its Carter constant is changed. Now, what I show here in this plot is essentially the maximum change in these parameters that you can get across a resonance. But of course, this is not, a generic value. So what do I mean by that? Right? Whenever we did this decomposition of the, say, the tidal force into these Fourier modes, it matters very much the initial phase which you enter the resonance, right? So at resonance, right, if I decompose or if I theta expand this near a resonance, right, I have some initial value q phi 0, saying q theta 0 and q r 0, plus omega times the time, etc. So the initial value that you have here, the term is actually the true size of the jump. So it could very well be that your phase is just fine-tuned enough that you exactly, you go through a resonance, but there's no kick whatsoever, right? Because somehow the jump size happens to be 0. Of course, you can also get a maximum case, as is the case here. So for the rest of the talk, of course, I'm going to assume, or look at the worst case or best case scenario, depending on your perspective, if you want to see these tidal resonances or not. But I'm going to assume that this maximum jump size.
Just a heads up, like you have I think roughly 10 minutes. Also.
Good. Okay, great. So what we then decided to do, right? So these calculations are semi-analytic, right, to most extent, right? So they're done using some approximations and in Mathematica to do the numerical integrations, but they are essentially semi-analytic. What we did is we compared these also with the case where we had some numerical klutz model that evolved the orbits, and we included the tidal field all throughout its evolution, right? So in these semi-analytic models, right, we only worry about the tidal field at the resonance, but here we just, added on the tidal field throughout. Of course, this model is extremely slow to calculate, but you can do it. And the very nice thing is that the jump sizes that we calculate agree remarkably well with this, numerical evolution. So this gives us confidence that what we did is, in fact, correct. And if we now look at the effect on the waveform, we again, will conclude that these things are important. And the way to do that is, well, you can either just construct a full waveform model from the get-go, but if you are a bit lazy, what you first want to make sure before you invest a lot of time in creating a proper waveform model is to see what is the phase difference that these tidal resonances induce. Right? Because if this phase difference is very small, then you might be, conclude, well, we don't need to worry about it, so let's not invest, our time in something else. But if this phase difference is, say, roughly larger than 0.1 radian, which of course depends a little bit on the signal to noise ratio, et cetera, but let's say for these M resources, if this is larger than 0.1, you should think of it as being observable, and if it's smaller, it's not. Now, what we do is, right, we compare the case where we have no tidal resonance to a case where we, a case where we have a tidal resonance to a case where we should have included a tidal resonance, but we somehow did not, and look at what this phase difference is going to be. And as it turns out, well, let's first look at the left figure. This phase difference, right, I've plotted it for you on a log scale. So being larger than 0.1 radian means that I should be larger than -1 here for it to be observable. And what you see is that for this, slowly spinning black hole and this particular type of resonance, this effect, right, is essentially observable pretty much for all of this parameter space, right? So as long as the eccentricity is larger than, this value or above this line, here this x is the cosine of the inclination, this effect is observable. Of course, I'm assuming some parameters here for, right, the mass of the central black hole and the distances, but of course, if you want some other values, you can easily rescale it. So here, I've taken, say, the mass of Sagittarius A star and at canonical distance of 10 AU to make this plot. But if you want any other values, you can easily change that and rescale your final answer. And this happens right across the parameter space. So, this was for a slowly spinning black hole. For a fast spinning black hole, right, the shape of the curves changes a bit, but the essential takeaway is, again, right, as long as we're larger than -1, this is observable. So pretty much across the parameter space it is. And this is the formula to tell you how to rescale it if you want to know the phase difference for different masses and distances. So the summary essentially of this part is that story 2, and I'll be super brief about story 3, is that tidal resonances will likely occur in MREs. And in particular, right, if we have data with a tidal resonance, if we are not correctly identifying it, right, we somehow do not model for this, we may incorrectly conclude that general relativity is incorrect, and we have some, signs of a modified theory of gravity. Whereas, I mean, what I believe we should do, of course, is that we should be very careful and take this into account and make sure that we model these resonances correctly. And when we do, I think, and actually see these systems, I think it will give us incredibly valuable information about the environment near massive black holes, right? Because this third perturber, it is, too far to be observed with gravitational waves, right? It's not in the Lisa band itself. We're most likely not going to see it with any electromagnetic observations, right? So there's no real way to measure that third perturber. But now we can actually see this extra perturber through its effect on the MRE. So I think that's pretty exciting. We get a whole, if we model this correctly, we get additional information of the environment near massive black holes. And this is still an ongoing story. We are following up with how to create proper waveforms and how much we can actually constrain these things. So there's a proper data analysis study on the way with Pete, Lorenzo, and Alvin. And we're also improving the analytic model by relaxing the assumption on the perturber being static, right? So because if you put this perturber a bit too close, then in fact you see that it is moving. So you should take into account at least, you know, some leading order effects of the fact that it is moving. So that was story 2. Maybe I'll just stop here and take questions, and I'll leave story 3 out altogether.